Okay, good afternoon. Today we're learning about Boolean operators and how we can combine them to make complex decisions in your if statements so that your programs can be more responsive and react to anything you want them to react to. We need to know the difference between and, not, and or in the context of Python programming, but also in flowcharts. But then we might also look at logic gates, and those logic gates are the building blocks of digital electronics, which is how a CPU actually works. So if you look inside your computer, you see the CPU. If you look inside the CPU, you'll see logic gates, and logic gates are just things that use electricity to make these decisions. Okay. We're going to look at truth tables and examples of how to do that in a mo. So George Boole invented a new way of doing maths which simplified things. Instead of big scary numbers, we've just got true or false. Remember last lesson we introduced the concept of true with a capital T, false with a capital F. I just want to look at examples. Yeah. Here is a truth table. Life is complicated. If you're faced with the decision of do I eat, I don't know, a sandwich with brie or do I eat a sandwich with camembert, it's a complicated decision. But Boolean logic simplifies things because it's either a yes answer or it's a no answer. So although this looks confusing, it's actually beautifully simple. Input A could be, am I hungry? Yes or no? No, I'm not hungry, as if that ever happens. Yes, I am hungry. Input B could be, have I got enough money in my bank account for a takeaway? No, I haven't. I'm not hungry anyway. Doesn't really matter that I'm not going to order a pizza. Am I hungry? No, I'm not. Have I got money? Yes, I have. Well, I'm not going to waste that money on a pizza because I'm not hungry. I don't really have that much self-control. I'll probably eat the pizza anyway. Am I hungry? Do I not have any money? I'm not going to order the pizza. Am I hungry? Have I got money? I am going to order pizza. Can you see how a truth table makes decision making simple? It takes the complexity out of life. Hooray, we've reduced the complexity of life into the simplicity of being a robot. We know when to order a pizza. So that was an AND gate. The only thing you need to remember is the output is only 1 if we have A and B. All of the other times the output is off. 0, false. An OR gate, this time we remember if we have A or B, the output is on. But also if we have A and B, the output is also on. So let's think. If you have 2 buttons, one on your desk, a panic button because somebody snuck into the room and is about to steal all of our food, we need to set the alarm off. Or there's another button on the wall somewhere where SLT can press it for a panic button test. If either of those buttons are pressed, the panic goes off, we have to go into the field and waste a little bit more time. Make sense? A NOT gate is simpler because you've only got one input, one output. Whatever the input is, the output is the opposite. So it's nice and simple. Sometimes called an inverter because it inverts the input. Remember 2's complement. 2's complement works in a CPU by having NOT gates. Whatever the input is, the output is the opposite. Okay. So if we're having a look at CT2 from half term 2, we call them logic gates or logical operators. Both AND and OR both have 2 inputs. A NOT gate only has 1 input. So AND is a 1 if both inputs are a 1. OR gives an output of 1 if either or both of the inputs are a 1. And NOT is the opposite. So we had these on the slides. The only one you need to be aware of for an AND gate is that one. Both inputs are on. Both inputs are true. Both inputs are 1. All of the others are zeros. Another way of remembering an OR gate is the only time the output is off is if both inputs are off. So all of the others are going to be 1s. And then hopefully you can do the NOT one yourself. It's nice and easy. It's really important that we cover those basics, whether we're doing it with electronics, discrete logic components, or logic operators in Python. So I've handed out these logic arithmetic things. Special thanks to the University of Southampton for providing these. You can switch it on at the top. You should get a little light. This is a Boolean switch, isn't it? A binary switch. It's either off or it's on. If it's on, we can see the light. If it's off, we can't see the light. There's no halfway in between. It's either on or it's off. So this is digital. Digital means we're dealing with ons and offs. We have some logic gates. This is an AND gate. Look, it looks like the D of AND. This is a OR gate. Look, it looks like a rocket going into orbit. Or this part, I should probably point with something less fat than my fingers. That part looks like half of an O. That's another way to remember it. And this is a NOT, which looks a little bit like a nose, a blob on a nose. It's the way that I can remember it. Or a NOT gate only has one input. Both of these have two inputs. You have some jumper leads. You can connect them to your inputs. So you've got some inputs here. Look, you can switch them on and off. 101. There we go. Come on, switch on. You can connect them. So if you get the pokey bit, the bit with a stalk, into the bit with a hole, like that, you can then plug those into the inputs of an AND. So look, my input L is on, so therefore my input to that AND gate is also on, and I can switch it off and on. How very exciting. And you can do the same with another one to the other input. There we go. So I've now got two inputs. The output is not on. Both inputs are off. The output is off. K is on. The output is off. L is on. The output is off. The output is only going to be on if both inputs are on. Just to prove that this happens in the real world with actual electronics. And if you combine these electronics in sufficient numbers and connect the output of that one into the inputs of others, you can make electronics count. And if you can make it count, you can make it do 2's complement, which means you can make an ALU, an arithmetic and logic unit, which is the building block of a CPU. So a CPU, a computer, is not magic. It is just these logic gates connected together in very large quantities. We're talking billions of logic gates. But you don't need that many. It's possible to make a gaming computer with only tens of these logic gates. We've got an example we could show you next lesson if you're interested. Obviously it's not particularly powerful. The more logic gates you have, the more power consumption it uses. This is only what? 16 logic gates, and it all runs off one battery. If you've got billions of them, it's going to use a lot of electricity, very low battery life, lots of heat generated. Okay. Okay, let's have a look at activity 2, because this doesn't look like the wires and connectivity, but it's the same thing. Here we've got an OR. It's not an OR gate, it's an OR logical operator. And we've got a Boolean expression. What on earth is an expression? Well, in maths, an expression is anything that contains numbers and functions like sine, cos, and tan and all of that kind of gubbins. In code, an expression is just any numbers, variables, and functions. Here we're saying 78 and 10, and we're comparing them. We're saying, are they equal? And you, as mathematicians, can instantly look at it and say, no, they're not equal. So that is false. 78 is not equal to 10. 6 is not equal to 7. So how does Python do this? Well, remember, it's probably worth debugging, actually, in Thonny. If we were to put that Boolean expression in here and to print it, we could run the whole thing. Oops, I'm trying to run it on a Raspberry Pi. Let's do local. There we go. We get false. But what does it actually mean if we debug it? No, I've got to save it first. So if we debug this, we're going to go through expression at a time. So I'm going to step into F7. Is that going to work? Debug nicer. Run, step into. Here we go. So I want to be able to evaluate this whole line. run, step into. In order to know what to print, I have to evaluate the expression inside the brackets. Press F7. In order to work out the expression in brackets, I need to do the expression in the inner brackets first. And in order to work that out, I need to know what 78 is. At last, there's something that we know what to do. It's just 78. I've also got 10. 10 is a literal value. It's just an integer. And we know what it is. It's 10. Now we've got two values. We know what they are. We're going to compare them. Are they the same? No, they're not. So we kind of replace that with false because they're not the same. Let's do the same on the other side. We've got two expressions. First of all, is this something we recognize? Yes, it's just 6. That is 7. As in, it's not a function that tries to calculate something. It's just the literal value 7. We compare them. They're not the same. So now, it's a truth table, isn't it? Two Boolean binary values combined with an OR. Have we got either or both? No, we haven't. So false or false is going to be false, which is what we then print. All of that happens just in one line, but sometimes it's helpful to step through and see each expression separately. So your job is to predict and then run it and see what happens. So copy and paste them in, see what happens. I'm going to do one more and leave you to do the rest. For example, is 6 less than 4? No, it's not. So that's false. Then we've got to do not false, which is true. So my prediction is not 6 is less than 4 is true. Let's test it. Got to be really quite logical to work these out. Excellent. How did it work? If you need some help, put it into Thonny, save it, debug nicer, and press F7. 6 is less than 4, so that's true. Oh, sorry, 6 is not less than 4. What on earth am I saying? 6 is not less than 4, it's false. And then the opposite of false is true. Great, you can do the rest yourself. So we're going to go through this one. If you're ever doing this in an exam, I would recommend that you do what I'm about to do. So you write out the Boolean expression, and then you just do what we saw Thonny do, and we're going to do it by hand. So is 1 less than 10? Yes, 1 is less than 10, so I'm going to replace that with true. Is 2 less than 10? Yes, 2 is less than 10. I'm going to replace that with a true or a 1. Then I've got a true or true, and in our truth table for or, if we've got both of them as being... Oh, look, there's a mistake here. Did anyone spot that? Oops, sorry. If both inputs are true for an OR gate, the output should be true or on. Should we test it and see? Put it into Thonny or create with code. We'll print the results. Yes, it's true. Brilliant. Let's move on. Activity 3. These are compound conditions. Compounds are not elements in chemistry. They are a chemical combination of multiple elements, aren't they? It's the same here. That's a Boolean expression, but it's a compound Boolean expression if you've got multiple logical operators. Gosh, this looks confusing. A compound condition. If count is less than or equal to 15 and not valid, or key equals k. So we've got all the different possibilities of 3 inputs. They can all be off, they can all be on, or any other possibility. They're just binary values. To work out this column, all we need to look at is this input, because not valid is the opposite of valid. That's 0, so therefore this is 1. That's a 1, so therefore this is a 0. So we've just inverted all of these to get these. This one looks confusing, but it's just not valid, that's this column, and key equals k, as in have we pressed the k key, that's this one, and we're combining them with OR. So it's basically an OR gate for these. So have I got either of these, or both of them? Yes, I have. Have I got either or both? Yes, I have. Have I got either or both? No, I haven't. It's just an OR logical operator combining these two rows. Sorry, these two columns. So this last one, we're combining count is less than or equal to 15, that one, and all of this nasty expression, but that nasty expression is just evaluated to, as in calculated to be, this. So, video paused. So for these, for example, we've got a 1 and a 1, so the output is a 1 on here. For our final activity, we've got some code here with a compound logical statement. We have to put in some values. Let's copy and paste it and run it and see what happens. Pop that in. Our first test value, attendance is 90%, 0.9. Have we missed any assignments? Yes, we have. I don't know what my prediction is. Just guessing. Let's see. Let's run it. So I have to put attendance in as a fraction, 0.9. It's not a fraction. Yuck. Number of missed assignments is 1, and it tells me I failed. It's a bit harsh. Why? Let's see. If attendance is greater than 85%, it is. That's good. And I haven't missed any assignments. Oh, that's where I failed. And I need both. This and this. I need them both to be true. So you can finish that table for me, please. So when you've done all you can on these worksheets, you want to save your Word document, save it into your Half Term 2 folder, close your Word document and upload it to Half Term 2 Algorithms and Programming 2 for me, please. Thanks for your hard work.